sensing and light emission on interesting surfaces, as well as things like smart packaging. And the idea is you take chemically engineered inks and run them through conventional printing processes by and large, and you end up with electronic devices. And I won't go into the great progress on the industrial side, but simply say that the printing technologies are kind of the workhorse of this growing industry. And arguably the simplest one is what's called relief printing, or now called flexography. Came initially by the Chinese about 2,000 years ago, where you were using wood stamps to print. One of the great manufacturing innovations in around the year 1500 was movable type, Gutenberg's invention of the movable type printing press. And the innovation was not just the press, but the method of making the letters by casting that enabled books to be mass produced. And then for, say, the past 100 years, a little bit less, we've been using rubber stamps to produce low-cost, large area graphics. And of course, we don't use as much print media as we did 10 or 20 years ago, but this is still a valid manufacturing process. And in the context of printing electronic materials, here's a sense of what's necessary to reach scale. This is a pilot line for doing flexography of a simple silver ink at a university in the US. And you saw the high speed. Hopefully the video is smooth, and that is an indication of the rate that you need. And that's just printing a sample conductive pattern here. And the flexography process involves the motion of a roller with a raised stamp, transfer of ink actually between 3 rollers, 2 steps of transfer, first a supply roller onto the stamp, and then second the actual print roller where you print onto the typically flexible substrate. Here it's an engineered paper. So the question is, what are the limits of this process in terms of the ink transfer? And you might think ideally you take a stamp with say a flat raised feature, call it a micro pillar, load ink on it, have a perfectly flat layer of ink, contact that to your substrate, and then you perfectly transfer a uniform ink layer. Maybe not all, but you split the volume as you predict. But of course, fluid mechanics make that not the ideal case. And in reality, when you try to make the features smaller, you run into issues such as film instabilities on the stamp if you're trying to load a very small amount of ink, i.e. a thin layer, the ink can de-wet. Or if you want to get good contact between the stamp and the substrate, you squeeze out ink due to excessive spreading. And that is compounded by non-uniform drying to say that the limit to the scale and resolution of flexography as a printing process is not the stamp features themselves. You can cast and mold polymers to sub-nanometer scales, but is the difficulty of loading and transferring thin liquid films. So we had the idea that we could perhaps control this process better by using nanoporous stamps instead of non-porous polymer stamps. So there is the idea of using carbon nanotube-based stamps. And in a carbon nanotube-based stamp for flexography, you load the ink within the stamp volume because the stamp is nanoporous. And here's a simple schematic of how it goes. We, of course, make pattern CNT structures on a silicon wafer, and then we engineer them such we can load them with a colloidal ink, and that allows them to be used in stamping. And therefore, we can transfer ink from not the surface of the stamp, or not just the surface, but from the volume of the stamp. And that turns out to be quite effective. Whoops. I'm sorry, I advanced too quickly, in enabling us to print very, very thin layers of ink. And the synthesis of CNTs in the form of these vertically aligned forests and vertically aligned microstructures is a topic of our great interest for many years, since I was a graduate student back at MIT, and we have understood how to control this well enough, at least, such that the CNT forest microstructures can be of uniform height and have a controlled architecture. And what I will show to you is it's really the architecture and mechanical properties of the forest and of the feature of each stamp that make this process possible, not only the bulk mechanics, but also the surface mechanics where the stamp contacts the substrate and where the ink is transferred. And we've also enabled this work by many studies of the CNT growth process. And here is some work done about 5 years ago using in situ TEM, environmental TEM, to look at the CNT forest growth process. And here we're looking down at a population of catalyst particles, and it just gives a sense of the self-organization of the CNTs that ultimately leads to the forest. So back to another version of the slide before the last one, where now you see the schematic of the process from left to right, and you see an example comparison of CNT stamp microstructures to printed ink patterns, and you see one stamp and one printed ink feature to show the fidelity we can achieve. What we saw early on, while we were still working out a lot of kinks and issues in uniformity, is that you can indeed get a printed ink pattern here measured by AFM to be very uniform. After drying of the liquid that contains the colloidal material in the ink. And you can also get it to have sharp corners, which is important if you're printing high fidelity features for sure. And to make these stamps work, we don't just have to grow CNT forests, but we have to do some surface engineering that we figured out. And the surface engineering is required both to enable the CNTs to be wetted by the ink and also enable the CNTs to be stable when they hold the ink. So now I'll show you a couple of videos. First, what happens if we take a drop of water and we evaporate it on non-reinforced CNT microstructures? They densify via capillarity when the ink infiltrates and then recedes. So beautiful process, but a bad one for what we want to do here. But after actually 2 consecutive surface treatments, after growing the CNTs, we plasma etch them to open up the top surface, and then we coat them conformally with a polymer. We can have stable nanoporous CNT structures. The video hopefully playing now shows liquid receding and the pillars remaining the same geometry. And that plasma etching step, I'll just say quickly, is also important because it removes what we call a crust layer of higher density CNTs from the top and enables the surface of the pillar to be the same mechanics as the bulk of the pillar, and that's important to have the compliance to get good contact between the stamp and the substrate. And compliance is important to get all the CNTs to touch the surface and therefore transfer the ink as a array of little tips, and also important over larger dimensions to accommodate roughness of the substrate. So then a simple experiment in creating something that has basic functionality is to print an array of lines using a line stamp. And here's not the stamp, but an array of silver lines printed from a colloidal silver ink, a commercial ink, and then sintered. And if you do sintering in a furnace, you can optimize the time and temperature and get electrical properties here, just DC, simple stuff, about 60% that of bulk silver. It can go a little higher, not to full bulk silver, but interesting enough for printing devices. And we spent quite some time studying the contact mechanics of the process. It's one thing to make the process work, another thing to understand how it works. And the best approximation is imagine the top surface of this wet CNT forest holding liquid. Like imagine a mountain range that was filled with liquid, but the liquid is sort of conforming to the surface of the mountaintops. Here the mountaintops are the CNTs, and here's a video through a microscope setup we built that's showing the contact of the wet CNT stamp with the substrate, and basically proves that as the contact evolves, all the CNTs contact the substrate you're printing on, you get a wet interface, and then you withdraw it and you get printing. And we worked out a relationship between the contact ratio, i.e. the fraction of the stamp area that's in contact, and the amount of liquid transfer, and you have a region of contact pressure, i.e. force per area, over the CNT pillar or CNT stamp, where you get good liquid transfer. And there's more on this in a paper in Langmuir that we published just last year. We wanted to also demonstrate a sort of scale up. So we built a machine. Danush, who finished his PhD last year, built a machine and studied these mechanisms for roll to plate transfer. So in industry, you saw a roll to roll machine. We built a roll to plate machine where you only have one roller, but this gives the same kind of contact mechanics. And another very quick video just showing the roller moving laterally at 200 millimeters per second, where you're getting transfer of ink between a CNT stamp on this flexure substrate and the roller where we'd wrap the compliant substrate for printing. So we can do things like print honeycomb type transparent electrodes, where you have a lot of open area, but you have solid area that's metal, and get good combinations of transmission and low sheet resistance over a visible wavelength range, and also apply this process to printing a variety of different colloidal inks. These are off-the-shelf semiconductors, dielectrics, et cetera. We haven't really pushed the limit in materials, but we certainly would be interested to do that, and also study the formation of multi-layer devices. And when it comes to where this process stands to what industry has done and academia has done, two charts here that I think are important. The first is the idea of this work was to do printing at a feature resolution that was in the single-digit microns. And as of the first paper we had demonstrated a resolution of about 3 microns, the smallest feature we made. And to do that at a process at a speed that is commensurate with what industry needs. So what you see on this chart are conventional printing technologies that offer decent resolution and high speed. And then down at the bottom left, really useful research technologies. And we can't compete with the resolution of individual tip printing, scanning probe tip printing, which is great for prototyping, but not good for production. Production, you need the speed of a fraction of a meter per second left to right it more. And then the chart at the right talks about ink transfer volume per unit length, which is a measure of the thinness of the layer that we're printing, and by our measures comparing to industry data and research where we were in good shape there. So that's how we demonstrated the novelty in terms of the performance metrics. So I hope I'll just take maybe 3 or 5 more minutes more talking about a complementary process, and that is now if you
we have about 4 minutes.
Sorry?
We have 4 minutes, so you have enough time.
4 minutes, perfect. Okay. A complementary process, if you think of what's needed to make an electronic device, you might print interconnects and maybe some sensing and energy storage areas, but you probably also want to put down physical components. And that's typically done, again, at high speed in industry by pick and place techniques. And here's a pick and place machine operating at several thousand components per hour. But I want to point you to one key thing. The minimum component size that these work with is say 100 microns or so on a side. And the reason why you don't mechanically pick and place components is not because they can't be made smaller, but because it's difficult to grab them mechanically, and surface forces overwhelm gravitational forces. When each of these machines grabs a component, it's a little mechanical gripper. So at a later stage of this flexography work, we started thinking of, could we use CNT forests for dry transfer printing and do dry transfer printing with the aid of electrostatics. So here I show you a basic experiment using a CNT forest pillar, just this block you see here, where the CNTs are not coated with a polymer as before, but they're coated with a thin ceramic, also a dielectric. And now we approach the surface of the forest with a scanning probe tip, an AFM tip with a microscale radius, and look at the force displacement curve, what we call the pull-off force curve, without voltage and with voltage applied, say voltage of 10 volts. And what you want to see is down here, when we're in the regime where we're pulling the tip away from the substrate, you get a much higher pull-off force because you're inducing charge between the CNTs where voltage is applied and the tip, which is grounded. And therefore, you can effectively manipulate the adhesion between the tip and the substrate, which is the CNT forest. And what I will show you is the stamp in this experiment where we pick and place a 100 micron or so micro LED. So not the smallest micro LED, but we pick it up and we put it down. And what you're seeing is no grabbing from the side, but just applying voltage and turning that off and on. And why this is interesting is first, because with voltage, we can scale the adhesion, the pull-off force, in a predictable way. The force equals voltage squared, traditional sort of electrostatic attraction thing. But also because when the voltage is off, the nature of these surfaces gives them a very low contact area with the object. So you have a surface that has electrostatically switchable adhesion because of this, the charging effect, but also has very low off-state adhesion because the contact area is very, very small. The CNTs are very sparse. And by tuning this, studying this, it means we can pick things up with a high attraction force, but then we can turn off the voltage and we can set them down. So small things, which don't weigh very much, don't stick to the stamp unless the voltage is on. And we demonstrated that for stamping of a wide variety of things. I'll say not individual structures, but sort of thin films and collections of structures ranging on the high end from these micro LEDs that we just bought from a supplier all the way down to films of nanowires. And we developed a model that talks about the balance between forces, being able to pick and place in terms of manipulating the stamp to object adhesion and the object to substrate adhesion. This is my last slide before I say thank you. When we think of what it's necessary to scale this process and what would make industry excited, beyond thinking of, hey, what are the applications, we need to understand truly how speedy it can be. How does it scale for both processes? I said, especially the scalability of making CNT stamps over large areas and controlling their patterning, as well as the robustness. You know, how many cycles can you do this over? How can you reload with ink? How many times can you compress? And so on. And if there's time for any questions, I'd be happy to take them on these or other topics. And thank you very much for your attention.
Thank you, John. Sorry, I lost my mouse, so it took me time to go to unmute myself. We have time for several questions, and Noah is asking, do you need to adjust the coating of the polymer to the ink? And also, what is the durability of these stamps?
Yeah, thank you, Noah. Great questions. We've used one polymer for all of the inks that we've studied before, but yes, in principle, you know, the polymer's surface characteristics would you know be necessary to, you could say, to be optimized to optimize the wettability of the ink, you know, and prevent the you know, if there's a volatile solvent it from affecting the polymer. The main thing we wanted to get right is the thickness and the deposition conditions. So we want the, you know, decent penetration and uniformity of coating, and enough coating to give the forest the right mechanics, but not make the forest too rigid. Durability, yeah, we haven't gone as far as we would need to go, but we've done hundreds and thousands of cycles of deformation, and actually we benefit from the resilience of the CNT forest, and in particular when we compress the forest and form some buckles at the bottom, those act as kind of springs that help the stamp be resilient.
And we have another question. We have another question by Daniel, which will be the last question for this talk, even though we have so many more.
Hi, John. Beautiful presentation. One quick question is, what's the role of the height of the nanotubes in this stamp? Because I assume the taller, the softer, but maybe other effects happen there. How did you adjust the height plays into this?
Yeah, so I think we found that sort of a middle height and middle aspect ratio, maybe stamp features of 3:1 or 5:1 height versus width worked best, because it let the CNT pillars, you know, be compliant enough to adapt to, you know, if our two surfaces were a little bit off parallel or you know, a little bit rough, without, you know, having them topple over or kink. So if you had very tall stamp features, there might be advantages, but then the features might be a bit more wobbly. Height can also have a role in the capillarity of ink transport, but we were fine given that we were working with shorter structures. And indeed we found that the ink, I gave you this cartoon of the ink sort of riding on the top surface of the stamp, but we did some imaging, both confocal and wet AFM, and showed that was the case. When we carefully load the ink, when we put just enough ink in the stamp, not too much. And if you get too much ink, you have excess, and you actually have to effectively blot away the extra ink from the stamp before you can get this, you know, this high fidelity printing that we show in our figures.
Thank you.
Thank you very much, John. I hope you can stay with us, and thank you again for joining us in such an early hour in the morning.
Thank you all.
So with that, let's go directly into the interesting stuff, where these nanoflorets are basically, as I said, are nanowires, which we modify with specific chemistry that occurs at the tip of the nanowire, where from the CVD growth, we have the gold catalyst, which changes locally the redox and chemical potential of the components, and therefore we are able to have this copper, silver, and gold, as I showed, nanoflorets, and we can further fine-tune the structure of the tip itself by adding, for example, thiols to the deposition solution. We can go from roughly 20 nanometer or 15 nanometer gold clusters, those, to very small, about 2 to 3 nanometer clusters here. And here you can still see the original gold nanoparticle used for the CVD synthesis of this silicon germanium alloy nanowire, which was then transformed into the Nano-Floret. So over the years after we published this synthesis in the JAX paper, we demonstrated chemical sensors and optoelectronic detectors, and now we work on a new type of detectors and devices, really. And we think this is a very interesting system because it combines all of these length scales where the nanowire can be quite long in the range of 1 to 100 or so microns, which is macroscopic. The diameter is in the 10 to 100 nanometer, and the length of the tip is from the tens to the hundreds. And then again, we can fine-tune the cluster size, and this gives a lot of opportunities to tune physical and chemical phenomena across scales and utilize it. So this is how it looks. We have the CVD synthesis of the silicon germanium alloy nanowire in the gas phase, and then in the liquid phase there is the deposition of the tip, as you can see here. This is in situ real-time stem measurements showing the tip deposition of the Nano-Floret. We have a quite detailed understanding of the mechanism, and it works on destabilization of the oxide of the alloy next to the metal-to-semiconductor junction, and therefore we need the small amounts of water to etch as an etchant to etch the oxide of the alloy, and then by galvanic displacement and catalytic tip deposition we have the deposition of the respective metal. And knowing all these parameters, we can tune the morphologies and properties of these tip selective attachments. So this is how the optical absorption looks of film of these nanoflorets. So we measured the nanowire, and then immediately after it is transformed to a nanofloret. And by a difference, you can see this very broad absorbency that goes all the way up to higher than 3 micron wavelength. And the reason it is cut at 200 and 500 nanometers is simply the limitation of the detector we had. So we utilize this broadband plasmonic absorption and tunable features to demonstrate near IR source enhancement, as you can see here, for example. And this was the opening to say if we have this near IR source enhancement that we can use in Raman spectroscopy, why can't we simply use it, because it's already coupled to a semiconducting nanowire in an optoelectronic device. And this is exactly what we did. So we simply grew these silicon germanium nanowires on titanium electrodes that are tipped structure, and those gap between the those bridge between the gap here. Now we can run put a potential across and check the conductivity as a function of illumination in the near IR. This is exactly what we did. This is how it looks in reality. So you can see the tip, which is a titanium electrode and counter electrode, and this nanoflorets with the metallic tip bridge over this gap. And now we measure the currents as a function of illumination, and we compare nanowires to nanoflorets. So because of the time, I will make it really short. Let's concentrate here on panel E. So you can see that as a function of wavelength, while detectivity and photoelectric gain of nanowires diminish at longer wavelength here, you can see that for the nanoflorets, it is stable and even increases at the near IR. And this was an opening for a whole bunch of architecture that can utilize this bridging effect with the nanowires that are coupled with a plasmonic antenna at the tip. We also modeled the response, the optical response of this tip, and we could account for the long wavelength absorbance in the near IR, which depends on the exact interfacial structure of the clusters, which is not just metal-to-metal interaction, but there is the electric layer, very thin, the electric layer between them. And this is the long wavelength response is owing to the collective response of this as an ensemble. So the next was to use the exact same architecture I showed you with the gap bridging, but now instead of shining light on it like we did before, now simply let molecules intercalate between this tip and the counter electrode and see if we can get molecule-specific information out of it. So this is a way to actually make self-assembly structures for making nano gap detectors that are usually require ultra high vacuum, elaborate setup, and so on, as everybody knows about metal break junctions and so on. However, this is a very simple method. It can be applied using very scalable and simple methods. And most importantly, it's operational under ambient conditions, under liquids, solvents, and I hope I'll get in time to show you that we can even measure in water. So this was the first demonstration of such a nanogap detectors. And what we did here, we took amine thiol molecules, and we took some quantum dots, cadmium selenide quantum dots, which has a specific band gap and fine structure. And we could really show that the density of states, the IDV, as a function of applied voltage in this device, is responsive towards the chemical species that are entrapped while you simply put a drop on it. And you can see here the typical gap for the quantum dots and even fine structure of the SP transitions. All of this was measured in ambient conditions. Next, we wanted to utilize same concept, but for liquids. So here we changed the design. Instead of having this tip design, we wanted to have large surface area. So now we have a concentric design where we have a central electrode. You can see a SEM image here. And this Nano-Florets contact the counter electrode, which is concentric. We add passivation layer, so it will be operable under liquids and so on. And this is what you get. So you get that once you put molecules that has specific affinity to the gold tip, the currents diminish as you increase the molecule concentration. This is kind of a conventional, you could do this with any conventional sensor. It's nice, but not very interesting. What else you could do? You could do real-time measurements and follow the adsorption. And if you look very carefully, you'll see a kink here. So this kink is not noise. This is a reorientation of the monolayer as a change of coverage, where this sensor is very sensitive. But the really interesting stuff comes here. This is what I show you. Using this in aqueous solutions, in buffers, or in organic media, doesn't matter really now. You can get band gap evolution of the IDV curve as a function of chain length, and you can see here the fit. Furthermore, for different molecules, not only see the decrease in current, but in each data point, you can really take the IDV spectrum, and you can see how the IDV data evolves with concentration. And this is already fingerprint detection of the normalized DIDV curves for different analytes. And right now, we are in the process of making machine learning algorithms and factor analysis tools to really have detection capabilities with this kind of arrays of detectors for any random mixture of molecules. So nowadays, we are at the point where we can really say that we have water-compatible electronic tunneling spectroscopy detectors, which are manufactured by very cheap and scalable methodologies. So I think, yeah, this is my last slide. Thank you, everybody, and I hope that we have some time for a couple of questions.
Thank you very much, Roy. You're just in time, actually. Amazing. Great work, beautiful work. Do you have questions? Actually, I had several questions. Oh, Chagai, yeah.
Yeah, does the fingerprint match the vibrational modes, or is just, I mean, what is the basis for these modes in IDV?
Yeah, thank you for the question. So this is a very interesting point. The fingerprints that we get are technically they are the IDV curves. However, they are not directly the isolated vacuum measured density of states of the molecule on the one hand. On the other hand, it is really measured in solvent environments and for ensembles of molecules assembled at the interface. So on the one hand, this is not the simple tunneling data that you would get from an isolated molecule. However, we believe it is very informative because it takes into account all the, like you suggest, vibrational interactions. It takes also solvent solute interactions and so on. And we think it's not just a sensor, but it's also a tool, a research tool. For example, we envision looking into proteins in real buffer environments and see how their electron conduction mechanism vary in response to changing conditions. So we think it's a very broad platform for the future.
Are there any other questions? So if not, I will ask one short question. So what is the mechanism that goes there in the interface? Is it the electron moving, or is it hole transport between the gold and the silicon?
Okay. Yeah, so this is electron transfer mediated by the molecular assembly at the interface. We have results that we have not published yet, where we also can demonstrate mediation by proton transfer. So basically you have a platform that is sensitive to electron and any charge carrier transport at the interface across monolayers. And the details really depend on what you put in the interface.
Really fascinating. So I would like to thank Roy. We're out of time. We have to go to the next speaker. And our next speaker is the first contributed talk of today, is Rakefet Ofek Almog from the Israeli College of Engineering. And Rakefet, let's try to see just that you managed to go with the presentation. Great, we see the presentation.
Okay. Okay, great.
All right, great.
Okay,
so
thank you.
Please, Rakefet.
Okay. Hi, my name is Dr. Rakefet Ofek Almog. I'm from Israeli College of Engineering, and today I'll talk to you about decorating ZNO nanowalls with gold nanoparticles for biosensing application. This research has just started recently, and it's in collaboration with Tel Aviv University, Professor Yossi Shachan's group. So, the survival of future generation depends on the evolution of sustainable society. And among the key factors in sustainability is the data-driven agriculture and the monitoring of both food and water. The Internet of Things is a powerful scheme to transfer the data from the field to the cloud. However, it requires an enormous amount of sensors that should be robust, low cost, low power, biocompatible, and can be integrated onto existing technology in order not to be too expensive. The aim of our research is to develop a biological sensor, especially due to the international aspects of sustainability in underdeveloped and in developing countries. So the main objective of this research is a biosensor based off ZNO nanowall decorated with gold nanoparticles. The proposed research aims toward the development of a highly sensitive and selective biosensor using relatively simple and low-cost materials and processing. The sensor will use recent advantages in fabricating electrodes of metal oxide nanostructures. But first, it has to be flexible. We heard a lot today about flexibility from the morning talks. So we know why we need it to be flexible and also cheap and robust. The ZNO is nanostructure semiconductor, high band gap semiconductor, and it should be decorated with functionalized noble metals such as gold. Why ZNO? The biocompatibility, the low toxicity, the high electron mobility, and the ease of fabrication makes ZNO well suited for biosensing. And the whole thing should fit into one novel all-in-one biosensor. That's the main goal, a flexible all-in-one ZNO-based biosensor. We deposited the ZNO on two substrates. First, silicon. We all know what a silicon looks like, about a 1/2 or 1 micron thick silicon substrate. And the other one, in order to be flexible, we deposited the ZNO on polyimide sheets. Polyimide about 100 micron thickness. This is how a polyimide sheet or wafer looks like. We have a lot of experience in Yossi Shacham's lab in depositing on polyimide on flexible substrates. This is an old version about photolithography process on polyimide. However, the yield modulus it's quite high for polymer, about 3 gigapascals. So it's robust, it's strong. However, it is still very soft comparing to silicon. On the substrate, if it's silicon or polyimide, nevertheless, we need to deposit the ZNO on a layer, a seed layer. If we did not deposit on an aluminum seed layer, we get nanorods. And if we deposit on aluminum seed layer, we get nanowalls. And the thickness of the wall is about 20 nanometers. And the advantage of nanowalls on nanorods is the large surface to volume ratio. If we want to make it a sensor, we need a very large surface area. So we prefer the nanowalls rather than the nanorods. These are 2 images of the ZNO nanowalls on silicon substrate and on polyimide substrate. And you can see that we did it okay on both. You can hardly tell the difference. The advances as in crystal growth technology allows obtaining ZNO nanostructure of various sizes, shapes, and properties. And this plays a crucial role in effective immobilization of biomolecules during biosensing. We deposited the ZNO on polyimide, and we also did Rutherford backscattering spectroscopy. Actually, it's in collaboration with a group in Italy, in Sicily, Catania University. And it was performed in RBS. And you can see the spectra of ZNO grown on aluminum titanium polyimide. The black line is the ZNO structure, and the red one is just the polyimide. And we tried different conditions. We did ZNO on both, this is just a polyimide. We did it both using stirring and without stirring. When it did exactly the same details, the same concentration and the same temperature, the same time, we got some nanorods when we did it with stirring and none when we did it without stirring. And it didn't matter how long, if it's 5 minutes or 30 minutes, but still we got better results without stirring. So that was our first conclusion, that without stirring is a better way to deposit on polyimide at least. So we don't want to get nanorods because the surface area is smaller. the next step that we wanted to do is to deposit gold nanoparticles. However, we did it in parallel. So we did a gold nanoparticle electroless deposition before we managed to do the good nanowalls. So here you can see deposition of gold nanoparticles, electroless gold deposition for different times, from 2 minutes to 30 minutes. But the ZNO is not a nanowall at all, it's hardly nanorods, some kind of nanostructure. However, we studied the deposition rate of gold on nanoparticles, and we will repeat it now that we know how to make good nanowall structure. Now we can do it on the nanowalls themselves. And we concluded that the best time was 10 minutes, but we'll have to repeat it on the nanowalls. We don't know if it's going to be the same times exactly, because the surface area is very different. What next are we going to do? We want to make these construction to be tested on ethylene sensors. Detecting ethylene gas from plants is very important for as I said, I don't have time to explain all the details, but it's good for agriculture. And so the detecting will be done on ZNO nanowalls decorated with gold nanoparticles. We believe the decoration of a metal oxide nanostructure with noble metal nanoparticles will enhance the electrochemical performance of the sensors. So how will we do it? We'll make some kind of different electrical structure, such as a Van der Pau structure. We have done it before, but not with nanowalls. So now it's the first time we're going to do it with nanowalls. And the next thing will to make a different electrical device and to study how the electrical resistance changes while the ethylene is absorbed on our ZNO structure. So the changing in resistivity will be the sensing of ethylene. So to summarize what we did and what we will do in the future, ZNO nanowalls were deposited on both silicon oxide and polyimide. We did Rutherford scattering and SEM for different conditions, different times, concentration, steering, without steering. And we think that the new electrode can serve as a flexible electrode for biological sensing. And we also, in parallel, we studied a gold nanoparticle deposition, electrical deposition on ZNO nanostructure. Now we want to combine the two things, the electroless deposition of gold on nanowalls, ZNO nanostructure, and we'll do electrical characterization, ethylene sensing, and we believe that this new structure should be further explored to reveal its full potential for a flexible biosensor application. I'd love to answer some questions if you have any, because 10 minutes is really short. So
really short, yeah,
yes,
definitely.
So I'm not sure I could explain everything. So if you have questions, I'd be more than happy to answer.
So we do have time for 1 or 2 questions. So, okay, but I would like to ask, so you're going to first use it as a gas sensor, if I understand correctly.
Yes.
What about going towards liquid environments, aqueous environments?
We also think about it, yes. Actually, we have a proposal to the BSF now that we're talking both about wet and dry sensors. So yes, we are definitely thinking about both these things. It will be a bit different in dry and wet conditions, but yes, definitely this is one of our directions.
Okay, excellent, great. So if there are no further questions, we'll move on. Actually, we are already quite late with the schedule, so let's move on to our next contributor speaker. Our next speaker is Udi Greenberg from Bar-Ilan University. Udi, can you try and upload? Oh, like if you need to
I have to stop sharing.
Release,
so.
yeah.
Okay.
Okay, you're on. We can see you.
Okay.
So please, Udi.
So hello everybody, my name is Ehud Greenberg and I am a PhD student from Bar-Ilan University, and I will talk today about a new method for 2D and 3D printing based on laser-induced photothermal reaction. As we know, and as we can see here, there are many techniques for 2D and 3D printing that could print a various structure for the various applications, such as for implants or electrical devices and more. But there are some disadvantages with those techniques. The first problem is that some of those techniques are very limited with the materials that they could print. For example, the UV technique requires only a polymer that's sensitive for UV light. The second problem is the minimal feature size that this technique could print, that between 10 to 100 microns. So if we want to make some structures that's smaller than 10 micron, this technique could not be our option. The last problem is that some of those techniques require a post-processing, such as annealing or remove the material supporting the printed during the 3D printed process. So our motivation for this research is first, to develop a new method that could print a various material. We want to reduce the minimal feature size to 1 micron, and we want that our technique did not require any post-processing. So how our system is looked. Eventually we use with a modulated continuous wave laser that directed to a microscope. The laser beam is focused on the metal ion solution droplet that's placed on the sample, on the substrate. So here in this small area, we get our pattern or structure. So finally, we need only to wash the metal ion solution and we still with our pattern or structure. So in the first step in our research is to understand the deposition mechanism in our technique. So we saw that we have a microbubble involved in our process, and the deposition occurs at the interface between the gas, liquid, and solid from the microbubble metal ion solution and the substrate. So we are thought that the best way to understand the deposition mechanism is to know what happened at the different interfaces. So we suggest to separate our process to 3 different cases that depend on the different interface. So the first case is when the laser is focused on the edge of the metal ion solution droplet at the liquid and gas interfaces. And as we can see, we get a deposition. We took this deposition to the high resolution TEM to analyze the nanostructure of this deposition. And we found that the nanostructure of this deposition was amorphous. The next case is when the laser is focused inside the metal ion solution droplet at the liquid interface. And as we can see, we got metal nanoparticles. We also took those metal nanoparticles to the high resolution TEM to analyze their nanostructure. And now, as we can see, we found that the nanostructure was with a crystalline shape. So the last case that we are investigating is when the laser is focused on the substrate at the liquid, gas, and solid interface. As we can see here, we got some pattern by moving the microscope stage in X-Y axis. So again, we took this pattern to the high resolution TEM, and now, for our surprise, we got a mixture of amorphous and crystalline structure. So as we can see here in this image. So from this result, we conclude that the deposition mechanism in 2D is when the laser is focused on the substrate, it's lead to a local raised temperature and a microbubble is formed. Convection flow around the microbubble carried some of the crystalline nanoparticle to paint at a microbubble substrate interfaces. And also in this local area of this interface, the amorphous structure is also formed. So finally, we get a mixture of crystalline and amorphous structure. Okay, so after we understood what happened in 2D, we want to know what happened in 3D. So also we made a 3D structure as a pillar, and we took it to the high resolution TEM. And again, we found that we have a mixture of crystalline and amorphous structure. So we are understood that the 3D mechanism is similar to a mechanism in 2D. So after we close the issue with the deposition mechanism, we made some structure from various materials. So as I said in the beginning, one of our goal is to develop a new method that could print a various materials. So as you can see here, we succeed to make some structure, 3D structure from a various materials, silver, iron oxide, and platinum. So also in this paper that we published in our labs, we made some structure from a various material, such as polymer, MOFs, oxide, and metal. So from this slide, I want to show you that our technique is a very general technique. So in the next, we made some more complex structure. We can see here some bridge, spring, castle, and we can see also that we made some pillar with resolution of 900 nanometers. So we succeed to reduce the minimal feature size to less 1 micron. So here in this graph, we can see how we control the width of our structure by changing the laser power from 900 nanometer to 10 micron. So the last result that I want to share with you is that we also succeed to combine two different materials in the same structure. We made some pillar with a base of platinum and top from iron oxide. This result is a very unique compared to the other 3D printing technique. So I show you today a new method that could print various material with a high resolution of less 1 micron, and we don't need any post-processing in our technique. So thank you very much.
Thank you very much, Udi. We have several, we have time for several questions.
Yeah.
So I have at least one question, but I have several here written actually. So what is exactly the process that occurs there? So you're using ions in the solution, but how do you get the, why do they transfer to their metallic or ceramic phase?
It's a thermal, yeah, it's a good question. It's eventually it's a thermal process. By a local array temperature, we made a reduction or reduction of the metal to from ion metal to metal, or we collect nanoparticles. It's based. It's depend on the base of the solution that we use. But in this case, we made some reduction of our solution.
And when you presented several examples of using both salt, but when you talk about polymers, then what is the? So that's probably different.
Yeah. In the case of polymer, we printed a polyaniline, honey, and this is a little different process, but in this case, we start with a resin, and in this process, we made some polymerization of this polymer, or collection the oligomerium to a structure by the microbubble.
Excellent. Are there any further questions? So thank you very much, Udi, for this great work.
Thank you.
And our next speaker is actually for something completely different. Dr. Thomas Gilmore, I have to reach out, from Impedance Ltd. And actually, Thomas, I must say that initially I thought maybe I should refer you to the plasma session.
Yeah, it's
but then I figured, well, it's interesting enough. I don't care. I want you to leave in my session. So let's see first that we can upload your.
Trying to find my talk. So maybe if I open PowerPoint again, it will work. Let's share the screen. There it is. Yeah, mine is certainly going to be kind of an odd one out here. Everyone here is talking about this cutting edge, amazing, technology on a small scale. I'm going to be talking about like sort of sensors for semiconductor industry and for monitoring like industrial plasma processes. So it's in like several orders of magnitude bigger sensor, older technology, and so on. So I have to cover a lot in a short amount of time, so I'll go quickly. Yeah, Amit, thank you for the introduction. Let me start by saying like I'll introduce impedance very quickly. Some of you may know impedance already, but impedance is a little company based in Ireland, and we provide like commercial off-the-shelf plasma sensors. So like we have like Langmuir probes. Oh, let me turn on the laser pointer. So we make like Langmuir probes and deposition tolerant Langmuir probes and these VI probes and sensors that like are used for characterizing production plasmas. Basically, these are used for process development in the industry. And what I want to talk about today are the challenges that are going to be facing the industry in the future and how these technologies are going to be required to move on to the next semiconductor nodes. So very briefly, what are the challenges facing these like 10 nanometer, 5 nanometer, and 3 nanometer nodes? Firstly, there are things that impact product yield. So chambers are not so well matched. These huge, expensive plasma tools, they're very complex and they're not as well matched as you think. There's a lot of invisible wear and tear on these chambers that cause defects. So even cables that all look identical, they go through heat cycles and get damaged on the inside. You can't see this by eye, and it's hard to know that this problem has happened. And moving these very precise processes from the R&D production line to the across 50 different production lines is being a real challenge. So say getting the 5 nanometer node up and running took a lot longer than anticipated. Getting the 10 nanometer took a lot longer than anticipated. I want to show you why. And also people use previous generations of tools to try to make the new generation of processors and memory, which they lack the diagnostic sensors that they need. So I think the solution is to monitor the plasma directly. In terms of what people use these days for process monitoring, they usually they measure the forward and reflected power on their generators. It's quite a simple method, and it's not really accurate because it doesn't show you the power lost in the matchbox. So what's actually powering the process is the power you deliver minus what's lost in the matchbox, and that depends on the matchbox temperature and some other things. So it's quite a bigger variable than you realize. And pressure monitoring is misleading. You have this closed loop feedback control. So if you have an air leak, that hides that. Some people monitor the tuning capacitors in their radio frequency network, the matchbox, which is a rough measure of what's called the plasma impedance, but it's not good enough for 5 nanometer and 3 nanometer, basically. If you don't control it, you're going to lose the products. So what I want to introduce is what's called plasma impedance, and it's actually where the company name came from. This is a sort of basic schematic of a radio frequency network. You have your generator that supplies the voltage, and that's called the 50 ohm region. Then you have a matching box, and then you have a plasma. And here, there's a very, very simple model of a plasma. It has a capacitance due to the wafer. The wafer has a capacitance. The sheath above the wafer has a capacitance. You have collisions happening with electrons moving in the plasma. That's like a resistance. You have currents flowing. That's like an inductance. And also the walls and general condition of the chamber contributes to this equivalent circuit. So overall, this circuit has a total plasma impedance. And changes in anything in here will change the total plasma impedance, as in like the resistance that you measure, the number of ohms, the complex impedance. So let's have a look at what happens when electrons are moving in the circuit. This is some real data. So this is from the 50 ohm side. You have blue is the voltage wave, the voltage waveform, red is the current waveform. And they're pretty much 0 degrees phase between them. So 50 ohm region is designed to be like, to look like this. And then when you take a real measurement of what these waves look like from the plasma's perspective, they're entirely different. So you can see over here, you know, the voltage waveform is distorted a little. The current waveform is distorted a lot. There's a lot of what are called harmonic components because the plasma is a nonlinear load. So because of all these different components. So what you need to do for the future nodes is to measure this impedance, because if you want your process to be the same every single time, you want that impedance is the same every time. And wear and tear on the chamber or even different wafers will change these waveforms that you see. So you can use the plasma itself almost like its own diagnostic. Now, no one wants to compare one waveform to another. We can do something more practical. Take a Fourier transform of these waveforms and you get a harmonic spectrum. So what you're seeing here, like an optical spectrum with different wavelengths of light, here you have a spectrum with different wavelengths of radio frequency. So a very typical plasma frequency is 13.56 megahertz. So that's the first column here. And then the plasma itself will produce 27.12, 40.68, and all these other harmonics. And as you can see, the spectrum can be quite rich in a real production process. And what you find is that these you actually get a unique harmonic response depending on any fault that has happened. So if the capacitance of the wafer changes, or if there's an air leak, for example, you actually get different responses in the harmonics because the different circuit components changing. People who are a bit smarter than me can model that. I'm not super good at modeling that. But if you have a good model of the equations of motions of electron in your plasma, you can actually predict what this will be. So this is something that we monitor. We can provide these what are called VI probes that measure these voltage current waveforms, and they're flat, so they're designed to sit against the matchbox or be retrofitted inside, and they will measure this harmonic spectrum and they'll measure the impedance and everything else exactly. Or if you can't retrofit these into your tools, even what you can do is monitor radio frequency leaking out of the tool. So this is an antenna that's mounted on a window, literally looking at radio frequency leaking out. You get the same waveforms. Or you can put one of these antennas inside the matchbox. And more and more people, like as they're running into the issues of getting their processes, like their narrow process windows, like they have to stay inside these narrow process windows for these small nodes. They need to go to this level of monitoring in order to make sure they're not to keep the yield that they need. We have to go very quickly. It's only a short amount of time. So I'm going to give you an example of these sort of changes and how easy they are to see. This is taking all the harmonic data and impedance data from one of these sensors, and we're monitoring etching. So as you go from one layer to another in a process, you want to make sure that you can stop at the right time, so you don't over etch, or you don't go through too many layers, or you stop at the right distance in the layer. So that's called endpoint detection. You tell the plasma when I'm going to stop the process. And because a plasma can have this variation, you need to have a way of saying, like, you can't rely on time. The time will change each time you run the process a little bit. So you have to have something that tells the process when to end. So using radio frequency data, this is an example of endpoint detection for etch, in particular for when you're etching a very small amount of the wafer. So if most of the wafer is covered in hard mask and say only 1% or less of the wafer is exposed to the etching, that's very hard to measure optically. Normally you measure that optically. But the signal to noise ratio is very hard to get a reliable data. But there's a lot of publications that show RF and impedance monitoring is the way to go, because the capacitance of the wafer dominates the capacitance of the chamber. Like, it's actually the dominant component. So that change in the thickness of the wafer, the change in the capacitance, is quite easy to measure with these high frequencies, with the radio frequency you're powering. And there's been a lot of publications on this over the years, because let's say like Samsung and SK Hynix and all these companies are at the stage where they're making features so small that they need new detection methods, and this is, so they're showing that monitoring the impedance and harmonics gives you at least twice the sensitivity as optical sensors as you go to these small open area ratios. And the same technology can be used to monitor deposition. It's the same in reverse. So let me go to the next stage. We're going very quick. We're near the end. I want to talk about ion energy analysis. So what's actually happening inside you have a plasma and you have your substrate. You want to measure what's actually happening on your substrate, like what's really happening. And people normally rely on this after the fact wafer metrology. And what I think you need to do is directly monitor what your ions are doing. So there are these things called retarding field energy analyzers. and they're constructed something like this. So, and this has a very small dimension, like usually like sub-millimeter or like a couple of millimeters, because you don't want any collisions inside the analyzer. But essentially you have a series of metal grids with different voltages on them. And one of the grids, you vary the voltage to block ions. So when there's no blocking voltage, you collect all the current. At some point, you block all the ions coming in. And in between that, you get information on the ion energy distribution function. And that'll depend on pressure, frequency. It depends on the power you're applying, depends on the plasma density. It depends on a lot of things, controls this. But that is directly what's etching or depositing. Like it's a direct measurement of what's interacting with your wafer. For people who haven't seen this sort of data before, if you apply a radio frequency bias to a substrate, you actually, the ions don't come down at one energy. It's quite complicated. You get this peak splitting because the sheath is expanding and contracting. You get these little peaks down at lower energies because you get collisions in the sheath when the pressure is a little higher, and so on. And if your pressure changes a little bit, this will broaden. If your power changes a little bit, the central energy will shift. And if your plasma density shifts, the total ion flux will shift. So these are what you need to keep your process consistent. So many people in the industry actually develop their processes using this sort of technology, but it's impractical to use in a production environment because you have wires, you have to break vacuum, it's a metal wafer, and so on.
We have 1 minute, Thomas?
Yeah, 1 minute. Okay, we're nearly there. Also, these analyzers can be used for other applications, by the way. I just want to show off some publications from Israel. There's actually been quite a few where they've a lot of CubeSat characterization is actually done using these sensors. But anyway, what I want to announce is that we have now a wireless version of the sensor, which is battery operated, which is thin enough and light enough and battery operated, so it can load in through the normal load lock method and come back out. So you can now directly measure what's going on in a production environment. This is brand new. This is the first time this is announced publicly, by the way. I want to sort of show this off to the world, and I hope this can help the next generation of processing to get the yield it needs so that my phone runs faster. And that's everything. That was a race. Thank you very much.
Thank you very much. We have time for 1 or 2 questions. Actually, I wanted to ask, what is the resolution if you compare it to microscopy? What is the lowest difference in thickness that one can obtain?
Oh, actually, you can measure down on like a few nanometers thickness. Like there's papers that show like you can easily get like 1 micron resolution of thickness, but certainly lower than that with these sensors. I can point to publications if anyone's interested. There's been a lot of research into this area. Yeah.
Are there any further questions? If not, before I will thank, we're actually, we have some time for discussion about the things that we saw in this conference, in this session. And I just want to say that initially when I got to session this specific session, I was quite surprised that the organizers choose to combine together materials, assembly, and sensors. But actually, looking down now on the talks that we saw here, that went all the way from almost commercial or even commercial sensing towards commercial assembly, and all the way back to the initial points of how to really fabricate a sensor and how to test it. I think that it is obvious that these things do go hand in hand. So in academics, usually we're mostly interested in showing that something can identify something else, something can sense something else. But sometimes we forget that if we want it to get out to the public, we need also to think of how to assemble it and how to really, at the end of the day, build a device around it. And I think that some of the talks that we had here really covered all the different phases throughout the system. And one question, we have here several people that work with different kind of nanotubes from different materials. And we saw 2 talks here about using them either for printing or for sensing. And I wonder, are we going to see technology coming out of it? The famous question. So Reshef is already looking at me with a suspicious look because he already been there and done that. But where are we standing now these days? with sensors from this kind of materials. So Gili, maybe you can give us a little bit of where do you see this going?
Yeah, so I just want to share that I know that there is a startup company that came out of a technology developed at Sloan Kettering Center in New York, where fluorescent single-wall carbon nanotubes are used to detect lipid accumulations inside the cells. So this is already going into the industry, and in terms of finding commercial applications or biomedical applications that are interesting to the commercial or the public at large.
Recep, can you give us a little bit of insight on where inorganic nanotubes are in this field of sensing?
Well, the inorganic nanotubes are aiming at different applications, and I think there's room for everything, and we know that graphene has a lot of potential in many applications, perhaps even larger than carbon nanotubes. But in terms of the inorganic nanotubes and inorganic fluorine like nanoparticles, at the moment, the biggest application is, of course, in lubrication, and that has been spent off to the industry, and has been commercialized. But I think the biggest potential, at least for inorganic nanotubes, is in biomedical product, and not just that, in polymers and reinforced polymer. The reason being that they are non-toxic. This is one reason. The other reason is that they don't agglomerate so much, so they have a much easier way to disperse in the polymer. And they are not as strong as carbon nanotube for sure, but in terms of the engineering of production, they are as easy to produce as carbon nanotube. And on the other hand, they are much more from engineering point of view, they are much more easy to manufacture and to impregnate into the polymers. And there's a lot of interest now in the defense industry and in medical industry to put it in different polymers for different applications. And we work with Noah. Noah can comment on that and on the 3D printing of structures. And there is a lot. We are working now with other industries on the 3D printing of other polymers. There is quite a lot of potential due to these 2 or 3 facts that A, they are non-toxic, B, that they are easily dispersed, they are strong enough, and they can be used for a lot of different applications.
So Noah, Recep, let's put you on, and you're actually working with the 2 type of systems, so I will be happy to hear your thoughts about it.
So I work with carbon nanotubes, I work with inorganic nanotubes, I do biomedical and structural applications. I started getting into sensing applications lately. And I think if we're talking about getting nanoparticles in whichever form to the industry, the main problem lies within the upscaling, whether it's an upscaling of manufacturing or upscaling of assembly. And John, in the beginning of the session, shows a beautiful method of upscaling, for example, in nanochips assembly. So this is the bottleneck of getting this amazing performance into the wide world.
And in this sense, so I think Chagai and Udi, because you're both. So how do you tackle this problem of like taking something which you could do in the microscope and make it and upscaling it? So your system was really you can make specific features, but if you would like to make it into something like sensors, you do need to upscale it. So how can you do it with these kind of systems?
So I think that, there are things that you can do, like for instance, if you want to make very small sensors at very specific locations integrated in something, then you can use something like our methods. But the big answer should be that you have to combine different methods. So there's no one method that is perfect for everything. But if you think about combinations of microprinting with larger scale printing, these kinds of combinations could do the trick in the future. Because if it was a simple solution, then people would have figured it out by now. But
that's true. That's always the issue. All right, so I think we do have a lot of things to think about and to push forward this combination of sensors and the assembly and how to really do it. And actually we do it also in our lab, and we're trying to think, and we always struggle between these two different scales. But I think that here I would like to finish the session and really thank all of the speakers. I think we had a range of very interesting discussion from different type of sensing and applications and assembly. And I'm urging you to stay to the last few talks of the conference, which are really nice, like great plenary talks. So the plenary talk will continue at 3:30. So we have a little bit of a break to go and grab a coffee and relax a little bit. And I hope we'll see you in the next session. So thank you very much again for the speakers for the great talks.
Thank you very much. It was really interesting. Thank you, everyone.
Thank you very much.
Thank you very much.